The closest potentially habitable world to Earth is dying. 4 light-years away, orbiting the nearest star to our Sun, a planet roughly the size of Earth sits in what astronomers call the habitable zone. For years, scientists celebrated Proxima b as humanity's best hope for finding life beyond our solar system. Then the measurements came in. High-energy radiation bombards this world at levels 800 times greater than anything Earth experiences. Stellar winds carrying charged particles slam into its atmosphere at over 1 million miles per hour. Every single day, Proxima b loses tons of atmospheric gas into space, stripped away molecule by molecule by its own parent star. This is not a planet waiting for life to emerge. This is a planet being killed in slow motion. If you want to understand why our nearest cosmic neighbor faces inevitable destruction, hit that like button and subscribe. Now, get yourself nice and comfortable. Let's begin. The announcement came on August 24th, 2016, and it electrified the scientific world. Astronomers working at the European Southern Observatory confirmed the existence of a planet orbiting Proxima Centauri, the closest star to our Sun. This was not some distant gas giant orbiting a faraway stellar system. This was a rocky world roughly the size of Earth, sitting in the habitable zone of our nearest cosmic neighbor. For the first time in human history, we had found a potentially Earth-like world close enough that future generations might actually visit it. The discovery emerged from one of the most intensive observational campaigns ever undertaken for a single stellar target. Scientists had suspected for years that Proxima Centauri might host planets, but confirming their existence required patience measured in decades and precision measured in fractions of a meter per second. The team that finally succeeded had to separate genuine planetary signals from the noise created by the star's own turbulent surface activity. Scientists detected Proxima b using the radial velocity method, watching for tiny wobbles in the parent star caused by gravitational tugging from an orbiting planet. Every planet exerts gravitational force on its host star, causing the star to move in a small orbit around the system's center of mass. This stellar motion creates measurable shifts in the wavelength of starlight, as the star moves slightly toward and away from Earth. When the star approaches, its light shifts toward blue wavelengths. When it recedes, the light shifts toward red. The signal from Proxima b was faint, requiring sophisticated instruments and meticulous data analysis to extract from background noise. The planet causes its star to wobble at only about 1.4 meters per second, roughly the walking speed of an elderly person strolling through a park. Detecting such a minuscule motion across 4 light-years of intervening space represents one of the most remarkable technical achievements in modern astronomy. What emerged from those measurements painted an intriguing picture that captured the imagination of scientists and the public alike. Proxima b orbits its star at a distance of roughly 4.5 million miles, completing one full orbit every 11.2 Earth days. In our solar system, that distance would place a planet well inside Mercury's orbit, subjecting it to temperatures that would melt, lead, and vaporize most known materials. But Proxima Centauri is not our Sun. It is a red dwarf star, smaller, cooler, and dramatically dimmer than the yellow furnace at the center of our solar system. Red dwarfs burn their hydrogen fuel so slowly and efficiently that they can shine for trillions of years, far longer than the current age of the universe. Their dim output means that planets must orbit very close to receive enough warmth for liquid water, a proximity that carries consequences we are only beginning to understand. Proxima Centauri contains only about 12% of the Sun's mass, and emits barely 0.15% of the Sun's visible light output. From the surface of Proxima b, this star would appear as a dim red orb roughly 3 times larger than the Sun appears from Earth, but providing far less illumination. Noon on Proxima b would look something like deep twilight on our world. At 4.5 million miles from such a dim stellar furnace, Proxima b receives roughly the same amount of total energy that Earth receives from the Sun at 93 million miles. This coincidence of orbital distance and stellar output placed Proxima b squarely in what astronomers call the circumstellar habitable zone, sometimes called the Goldilocks zone, because conditions there might be just right for liquid water. The habitable zone represents the orbital sweet spot where temperatures might allow liquid water to exist on a planetary surface. Too close to a star, and water boils away into space, creating a runaway greenhouse effect like the hellish conditions on Venus. Too far, and water freezes into permanent ice, creating a frozen wasteland like the outer moons of our solar system. Proxima b appeared to thread this cosmic needle perfectly, sitting almost exactly in the center of its star's habitable zone. The implications seemed staggering to researchers who had spent careers searching for worlds that might harbor life. Here was a planet that might possess oceans, weather systems, perhaps even continents, and volcanic activity. The discovery suggested conditions that could theoretically support the kind of complex chemistry that leads to biological processes. Located just 4.24 light-years away, Proxima b represented the closest possible destination for interstellar exploration. Scientists and dreamers alike began imagining robotic probes that might reach this neighboring world within a human lifetime. The Breakthrough Starshot initiative had already proposed sending tiny spacecraft propelled by powerful ground-based lasers to velocities approaching 20% of light speed. At such velocities, a probe could reach Proxima b in roughly 20 years after launch. The discovery transformed this initiative from a technical demonstration into a potential reconnaissance mission to an alien world. Media coverage exploded across global networks within hours of the announcement. Headlines proclaimed the discovery of Earth's twin next door, though scientists cautioned that calling any world Earth's twin based on mass and orbital distance alone was premature. Artists rendered visions of alien oceans beneath red dwarf sunsets, imagining worlds of perpetual twilight where strange forms of life might thrive under dim crimson skies. Space agencies began discussing mission concepts that might someday photograph Proxima b's surface, or even detect signs of biological activity in its atmosphere. The James Webb Space Telescope, then still under construction, suddenly had a prime target for its powerful instruments. Future observatories might be able to analyze the composition of Proxima b's atmosphere by studying starlight filtering through it during planetary transits. The collective imagination of humanity turned toward this tiny world orbiting our nearest stellar neighbor. After decades of discovering exoplanets too far away to ever visit, too hostile to ever harbor life, or too large to resemble Earth in any meaningful way, Proxima b seemed to offer something unprecedented. A potentially habitable world close enough that the distance, while still enormous by human standards, at least fell within the realm of technological possibility. But amid the celebration, some scientists noticed troubling details in the data that tempered their enthusiasm considerably. The same measurements that revealed Proxima b's existence also revealed something far darker about its stellar environment. Proxima Centauri was not behaving like a gentle stellar host, nurturing a potentially habitable world. It was behaving like a violent aggressor, actively attacking its planetary companion through processes that had been operating since the planet formed. The first warning sign came from X-ray observations accumulated over decades of monitoring. Space telescopes including Chandra and XMM Newton had been watching Proxima Centauri since the 1990s, building a comprehensive picture of its high-energy output across multiple wavelengths. What they found should have tempered the optimism surrounding Proxima b's discovery from the very beginning. This tiny red dwarf star produces X-ray radiation at levels roughly 400 times greater than what the Sun delivers to Earth when measured at equivalent habitable zone distances. These are not gentle warming rays that might contribute to a pleasant climate. These are ionizing particles capable of stripping electrons from atoms and breaking molecular bonds in any material they encounter. X-ray photons carry enough energy to penetrate deep into planetary atmospheres and damage biological molecules directly. On Earth, Our atmosphere absorbs virtually all incoming X-ray radiation high in the stratosphere, protecting surface life from this invisible assault. Any world receiving 400 times our X-ray exposure would need an extraordinarily thick atmosphere to provide equivalent protection, and maintaining such an atmosphere under constant bombardment presents its own challenges. Even more concerning was the extreme ultraviolet output that emerged from careful spectroscopic analysis. Proxima Centauri bathes its habitable zone in extreme ultraviolet radiation at intensities that dwarf anything Earth experiences, by factors approaching 1,000. This high-energy light occupies wavelengths between 10 and 120 nanometers, invisible to human eyes but devastating to atmospheric chemistry. Extreme ultraviolet radiation does not simply warm a planetary surface the way visible and infrared light do. It actively attacks atmospheric molecules, breaking chemical bonds and giving molecular fragments enough energy to escape into space entirely. This process, called photodissociation, represents one of the primary mechanisms by which planets lose their atmospheres over geological time. But the true scale of the problem became clear only when scientists examined Proxima Centauri's stellar flares. Red dwarf stars are notoriously active, producing violent outbursts that briefly multiply their brightness by factors of hundreds or thousands. Proxima Centauri ranks among the most active stars in our stellar neighborhood, unleashing major flares every few days with energies equivalent to billions of nuclear weapons detonating simultaneously. These flares transform an already hostile radiation environment into something catastrophic. A planet sitting in the habitable zone of Proxima Centauri does not experience gentle stellar heating like Earth enjoys. It experiences periodic bombardment by high-energy particles and radiation that would sterilize any exposed surface and dramatically accelerate the loss of atmospheric gases to space. This brings us to the real problem facing Proxima b, a problem that transforms this world from a potential cradle of life into something far more tragic. The planet is losing its atmosphere, not slowly over cosmic timescales that might allow life to emerge and evolve before conditions deteriorate. Proxima b is losing its atmosphere continuously, relentlessly, at rates that compound over billions of years into an inescapable verdict of permanent uninhabitability. Understanding atmospheric stripping requires grasping how stellar radiation interacts with planetary atmospheres at the molecular level. When high-energy photons strike atmospheric molecules, they transfer energy to those molecules through various physical processes. Photons can be absorbed completely, transferring all their energy to molecular motion. They can ionize atoms, stripping away electrons and creating charged particles. They can break chemical bonds, fragmenting molecules into reactive components. If enough energy transfers to a molecule at the outer edge of an atmosphere, that molecule can reach escape velocity and leave the planet entirely. Escape velocity depends on planetary mass and radius. For a world roughly Earth's size, escape velocity measures about 11 kilometers per second. This process happens continuously on every planet, with an atmosphere exposed to stellar radiation. However, the rate of loss depends critically on the intensity of incoming radiation and the energy it carries. Higher energy photons are far more effective at accelerating atmospheric escape than lower energy visible light. On Earth, atmospheric stripping occurs at extremely low rates that pose no threat to our biosphere over relevant timescales. Our planet sits far enough from the Sun that high-energy radiation remains relatively weak by the time it reaches us. The inverse square law means that radiation intensity drops off rapidly with distance. At 93 million miles, Earth receives a relatively gentle bath of solar energy, with the most dangerous wavelengths representing only a tiny fraction of total output. More importantly, Earth possesses a powerful magnetic field that deflects most charged particles before they can interact with our atmosphere. This magnetic shield, generated by convection currents in our planet's liquid iron outer core, extends tens of thousands of kilometers into space and redirects the solar wind around our world, like water flowing around a rock in a stream. Without this protection, Earth would face far more severe atmospheric erosion. The combination of distance and magnetic protection keeps Earth's atmospheric loss rates negligible over geological timescales. We lose roughly 3 kilograms of atmosphere per second, primarily hydrogen and helium from the uppermost atmospheric layers. At this rate, Earth could maintain its atmosphere for trillions of years, far longer than the Sun will continue shining. Proxima b enjoys neither of these crucial advantages. Its orbital distance places it directly in the path of intense stellar radiation at close range, where every photon hits with maximum force. The inverse square law governing radiation intensity means that Proxima b receives roughly 50 times more high-energy flux than Earth simply due to its proximity to its parent star. Every photon of ultraviolet and X-ray radiation that Proxima Centauri produces hits this planet with dramatically greater intensity than anything our world experiences. The numbers that emerge from detailed analysis of this situation are devastating for any hopes of habitability. Conservative estimates suggest that Proxima b loses atmospheric mass at baseline rates exceeding 300,000 tons per year, even during quiet stellar periods. This baseline figure assumes only gentle thermal escape. During the frequent flare events and accounting for enhanced early stellar activity, loss rates spike by factors of thousands to millions, transforming steady erosion into catastrophic hemorrhaging. During major flares, which occur with alarming frequency on this active star, loss rates spike by factors of hundreds or thousands above already elevated baselines. A single powerful flare can strip away more atmospheric mass in hours than quiet conditions would remove in years. Integrated over the 4.5 billion years since Proxima b likely formed alongside its parent star, these losses accumulate into an inescapable conclusion. Even if Proxima b started with an atmosphere 10 times thicker than Earth's current atmosphere, sustained stripping at these rates would have removed most of that atmospheric mass billions of years ago. The planet we observe today has been subjected to relentless assault since its formation in the protoplanetary disk surrounding young Proxima Centauri. Whatever atmosphere it might have possessed at birth has been steadily stripped away, molecule by molecule, into the darkness of interstellar space. This is not a problem of orbital mechanics that might be solved by finding the right distance from the star. Moving Proxima b farther out would reduce temperatures below the threshold for liquid water, defeating the purpose of seeking habitable conditions. Moving it closer would only intensify the already catastrophic radiation exposure. This is not a problem of initial conditions that might be overcome with a sufficiently thick starting atmosphere. No plausible formation scenario delivers enough atmospheric mass to survive billions of years of sustained stripping at observed rates. The mathematics of exponential loss over geological time overwhelms any reasonable starting configuration. This is a fundamental incompatibility between red dwarf stellar physics and long-term atmospheric retention on closely orbiting planets. The very characteristics that place Proxima b in its star's habitable zone simultaneously subject it to an environment where no atmosphere can survive intact. The discovery of Proxima b did not reveal a potential second Earth waiting for life to emerge. It revealed a world being killed by its own sun through processes operating continuously across cosmic time. Consider what this means for any surface conditions on Proxima b today. Liquid water requires atmospheric pressure to exist in stable form. Below certain pressure thresholds, water cannot maintain a liquid phase regardless of temperature. Instead, it transitions directly from solid ice to gaseous vapor through sublimation whenever temperatures rise above freezing. This is why ice cubes shrink in your freezer, even though temperatures remain well below freezing. The water molecules escape directly into vapor without passing through a liquid state. As atmospheric pressure drops due to sustained stripping over billions of years, any surface water on Proxima b would gradually sublimate into the thinning atmosphere. Some of that water vapor would subsequently escape to space through the same processes, stripping away other atmospheric components. The planet would lose not just its air, but its water, leaving behind only frozen remnants in permanently shadowed regions that themselves would eventually be lost. The same principle applies to any complex chemistry that might serve as a foundation for life. Chemical reactions capable of building biological molecules require specific temperature and pressure ranges to proceed. Proteins fold correctly only within certain environmental windows. Lipid membranes maintain structural integrity only under appropriate conditions. Nucleic acids replicate faithfully only when their molecular environment remains stable. As Proxima B's atmosphere thins over geological time, the surface environment shifts increasingly toward conditions hostile to chemistry of any complexity. Even if life somehow emerged during an earlier epoch when conditions were less severe, that life would face steadily deteriorating circumstances as atmospheric loss continued. Eventually, surface conditions would become incompatible with biological processes of any kind. Scientists have attempted to model these processes using sophisticated computer simulations that track atmospheric evolution over billions of years. These models incorporate stellar radiation measurements at multiple wavelengths, planetary characteristics derived from radial velocity observations, and well-established physics of atmospheric escape, refined through decades of studying worlds in our own solar system. The results consistently point toward the same conclusion, regardless of starting assumptions. Researchers have varied initial atmospheric mass, composition, and temperature. They have explored different planetary magnetic field configurations. They have tested scenarios with enhanced volcanic outgassing and varying levels of stellar activity. The fundamental outcome remains unchanged across all reasonable parameter spaces. Proxima b cannot maintain a substantial atmosphere under the sustained assault it experiences from its parent star. The physics of atmospheric escape operating over geological time overwhelms any combination of favorable initial conditions or ongoing replenishment mechanisms. Some researchers have proposed potential escape routes from this verdict that deserve careful examination. Perhaps Proxima b possesses an unusually strong magnetic field that deflects incoming radiation and protects atmospheric molecules from direct stellar wind interaction. Perhaps volcanic activity continuously replenishes atmospheric gases faster than stellar radiation strips them away. Perhaps the planet started with such a massive atmosphere, perhaps one rivaling Venus in density, that billions of years of stripping have only partially depleted it. Each of these proposals faces fatal objections grounded in established physics and observations. We will examine these counterarguments in detail in subsequent sections, showing why none of them can rescue Proxima b from its ultimate fate. For now, understand that the fundamental physics of atmospheric stripping operates independently of these factors. Even with magnetic protection, even with volcanic outgassing, even with enormous initial atmospheric mass, the sustained radiation environment around Proxima Centauri drives atmospheric loss at rates that cannot be overcome through any known mechanism. The measurements that confirmed Proxima b's existence simultaneously confirmed its doom. This is not speculation about what might happen in some distant future that humans need not worry about. This is recognition of a process that has been operating continuously for billions of years, that operates today as you read these words, and that will continue operating until whatever remnants of atmosphere this world possesses have been entirely lost to space. The stripping began when Proxima b formed from the swirling disk of gas and dust surrounding its young parent star. It continued through whatever early epochs might have briefly hosted more favorable conditions. It operates now at rates we can measure and model. It will continue until nothing remains to strip. Our nearest potentially habitable neighbour is not a world awaiting the emergence of life beneath alien skies. It is a world where the conditions for life have been systematically destroyed by stellar processes operating over cosmic timescales. The habitable zone around Proxima Centauri exists only in the abstract definition of orbital distances where temperatures might theoretically permit liquid water. In physical reality, no world in that zone can retain the atmospheric conditions necessary for genuine habitability. This realization transforms how we must think about the search for life beyond Earth. The exciting discovery that sparked global celebration actually revealed something far more sobering about the cosmic neighborhood we inhabit. Proximity to a star is not sufficient for habitability. Orbital position within a theoretical habitable zone is not sufficient for habitability. The stellar environment itself must permit long-term atmospheric retention, and red dwarf stars like Proxima Centauri create environments where such retention appears physically impossible for closely orbiting rocky worlds. The closest potentially Earth-like world to our solar system is being stripped bare by its own parent star through processes we now understand in considerable detail. Understanding how this destruction unfolds requires examining the violent behavior of Proxima Centauri far more closely than the initial discovery announcement suggested. The assault on Proxima b's atmosphere operates through multiple mechanisms simultaneously, each contributing to the relentless loss that dooms this world to airless sterility. What comes next reveals the full scope of the stellar violence that Proxima b endures every single day of its existence, violence that has continued without pause since this world first formed, and that will continue until nothing remains but barren rock beneath empty skies. Proxima Centauri appears almost invisible to the naked eye, despite being the closest star to our Sun. Standing under perfectly dark skies far from any city lights, you would need to know exactly where to look and possess exceptional vision to glimpse this stellar neighbor as anything more than empty darkness. This tiny red dwarf contains only 12% of the Sun's mass and emits barely 15/100ths of 1% of the Sun's visible light output. From Earth it requires a telescope to see it all, lost among the background stars of the southern constellation Centaurus. Yet this seemingly feeble star generates violence that dwarfs anything our planetary system experiences. The contrast between appearance and reality defines everything about Proxima Centauri's relationship with its planets. What looks like a dim cosmic ember actually behaves like a continuous explosion, releasing energies that would sterilize any unprotected world within its reach. Red dwarf stars like Proxima Centauri operate under fundamentally different physics than Sun-like stars. Their smaller mass creates lower core temperatures and pressures, resulting in nuclear fusion rates far below what powers larger stellar furnaces. The Sun's core reaches temperatures exceeding 15 million degrees, driving hydrogen fusion at rates that produce the brilliant yellow light we see from Earth. Proxima Centauri's core barely exceeds 3 million degrees, fusion proceeding so slowly that this star will continue burning for trillions of years after our Sun has died. But the most consequential difference lies in how energy moves from core to surface. The Sun possesses a layered structure with a radiative zone surrounding the core where energy travels outward through photon absorption and re-emission. Only the outer 30% of the Sun's radius experiences convection, with hot plasma rising and cool plasma sinking in circulating currents that transport energy to the surface. Red dwarfs lack this radiative zone entirely. Their smaller mass and lower temperatures mean that convective energy transport dominates throughout their entire interiors. From the nuclear burning core to the visible surface, hot plasma churns upward while cooler plasma sinks in a continuous roiling motion. The entire star behaves like a boiling pot of water, rather than the layered structure of larger stars. This total convection creates magnetic field configurations far more complex and unstable than those of Sun-like stars. Magnetic fields in stellar interiors arise from the interaction between convective motion and electrical currents in the ionized plasma. The Sun's magnetic field emerges primarily from the boundary layer between its radiative and convective zones, creating relatively organized field structures that follow predictable 11-year activity cycles. Proxima Centauri lacks any such organizing boundary. Convective cells throughout the entire stellar interior generate tangled magnetic field configurations that twist and reconnect unpredictably. The resulting magnetic activity far exceeds what our Sun produces, despite Proxima Centauri's much smaller size and lower luminosity. This hyperactive magnetic field drives the violent behavior that makes this star so hostile to any orbiting planets. The magnetic activity of Proxima Centauri manifests most dramatically through stellar flares visible across interstellar distances. These explosive events occur when twisted magnetic field lines suddenly reconnect, releasing enormous amounts of stored magnetic energy in seconds or minutes. Magnetic reconnection converts field energy directly into kinetic energy of charged particles, plus electromagnetic radiation, spanning the entire spectrum from radio waves to gamma rays. The physics of magnetic reconnection operates similarly on our Sun, producing solar flares that occasionally disrupt satellite communications and create beautiful auroral displays at high latitudes. But the scale and frequency differ enormously between our stable yellow Sun and the violent red dwarf next door. Solar flares of the largest category occur perhaps once per solar cycle, roughly every 11 years. Proxima Centauri produces comparable or larger events every few days. Observations, spanning decades, have revealed just how violently Proxima Centauri behaves compared to our relatively peaceful Sun. Major flares occur roughly every 3 to 4 days on average, each releasing energies that would qualify as exceptional events if they occurred on our Sun. Superflares capable of briefly increasing the star's brightness by factors of thousands erupt several times per year, dwarfing anything recorded in the history of solar observation. The most extreme events recorded from Proxima Centauri have released energies equivalent to trillions of nuclear weapons detonating simultaneously. These stellar explosions briefly outshine the star's normal output by factors exceeding 10,000 in certain wavelengths. The radiation pulse travels outward at light speed, reaching Proxima b in roughly 25 seconds and bathing that world in a lethal dose of high-energy photons. During the massive flare observed on March 24, 2017, Proxima Centauri briefly became 1,000 times brighter than its normal output across multiple wavelengths. This event released approximately 10 to the 33rd ergs of energy in less than 10 minutes, comparable to the total energy output of our Sun over several days, concentrated into a single violent pulse. Scientists calculated that Proxima b received roughly 400 years' worth of normal stellar radiation during those few minutes of peak flare intensity. Any atmosphere exposed to such an event would experience heating and ionization effects that dramatically accelerate atmospheric escape processes, already operating at alarming rates during quiet periods. The outer atmospheric layers would expand rapidly as molecules absorbed enormous amounts of energy, with significant fractions reaching velocities sufficient to escape the planet entirely. Subsequent analysis of this flare event revealed additional concerning details. The radiation pulse was accompanied by a coronal mass ejection, a massive bubble of magnetized plasma expelled from the star's outer atmosphere at velocities approaching 2,000 kilometers per second. This plasma cloud would have reached Proxima b within hours of the initial radiation pulse, compressing any planetary magnetic field and directly bombarding atmospheric molecules with energetic particles. But flares represent only the most visible and dramatic component of Proxima Centauri's assault on its planetary companion. Even during quiet periods between flares, this red dwarf produces high-energy radiation that steadily erodes atmospheric stability through processes operating continuously without interruption. The extreme ultraviolet spectrum deserves particular attention because of its central role in driving atmospheric escape. Radiation in wavelengths between 10 and 120 nanometers carries enough energy to ionize atoms and break molecular bonds in virtually any atmospheric constituent. These photons are invisible to human eyes, but devastatingly effective at disrupting the chemistry that holds atmospheres together. Proxima Centauri produces extreme ultraviolet radiation at intensities roughly 60 times greater than the Sun delivers to Earth when measured at equivalent habitable zone distances. This comparison already accounts for the different orbital distances involved. At Proxima b's actual orbital distance of roughly 7 million kilometers, the extreme ultraviolet flux translates to roughly 1,000 times what Earth's upper atmosphere experiences from our Sun. This extreme ultraviolet radiation penetrates into planetary atmospheres and deposits its energy primarily in the thermosphere, the uppermost atmospheric layer extending from roughly 85 kilometers altitude to the edge of space on Earth. The thermosphere exhibits a counterintuitive temperature profile, with temperatures increasing rather than decreasing with altitude because solar radiation deposits energy directly into this tenuous region. On Earth, thermospheric temperatures reach roughly 1000 degrees Kelvin during periods of high solar activity, though the extremely low density at these altitudes means this heat represents minimal total energy. On Proxima b, extreme ultraviolet heating would drive thermospheric temperatures far higher, potentially exceeding several thousand degrees depending on atmospheric composition and density. As extreme ultraviolet photons are absorbed by atmospheric molecules, they transfer their energy in several ways. Some photons ionize atoms directly, stripping away electrons and creating charged particles. Others break molecular bonds through photodissociation, splitting stable molecules like water or carbon dioxide into reactive fragments. Still others simply heat gas molecules, increasing their random thermal velocities. Hot gas expands according to fundamental physics. At sufficient temperatures, molecules at the outer edge of the thermosphere gain enough kinetic energy to exceed escape velocity and leave the planet entirely. This process removes atmospheric mass continuously whenever the thermosphere is heated above critical temperature thresholds that depend on planetary gravity and atmospheric composition. Scientists call this process hydrodynamic escape. When it operates at high enough rates that individual molecular escape gives way to bulk atmospheric outflow. Rather than occasional molecules randomly achieving escape velocity through thermal motion, entire portions of the upper atmosphere flow outward in a continuous wind of escaping gas. The atmosphere literally boils off into space like steam rising from a heated pot. Hydrodynamic escape can remove atmospheric mass thousands of times faster than the molecular escape processes operating on Earth today. Our planet loses roughly 3 kilograms of atmosphere per second, primarily hydrogen and helium from the uppermost atmospheric layers. A planet experiencing hydrodynamic escape might lose thousands or millions of kilograms per second, depending on stellar energy input and planetary parameters. Models of Proxima b's atmospheric evolution suggest that hydrodynamic escape likely dominated during the planet's early history, when Proxima Centauri was even more active than it is today. Young red dwarf stars produce extreme ultraviolet radiation at levels far exceeding their mature output, sometimes by factors of 10 to 100 compared to their eventual stable luminosity. This enhanced early activity stems from faster stellar rotation in young stars, which drives more vigorous magnetic dynamo action and correspondingly more intense magnetic activity. As stars age, they gradually spin down through magnetic braking, losing angular momentum to their stellar winds. This slowdown reduces magnetic activity and associated high-energy radiation over timescales of hundreds of millions to billions of years. During the first few 100 million years after Proxima b formed, escape rates may have exceeded current levels by factors of 10 or more. This early epoch of catastrophic loss would have removed enormous amounts of atmospheric mass before the star settled into its current activity state. Atmospheres that might have started with masses comparable to Venus could have been stripped down to thin remnants within the first few 100 million years of planetary history. This brings us back to the real problem that dominates Proxima b's fate: accumulated loss over geological timescales that dwarf human comprehension. Even if hydrodynamic escape rates declined as Proxima Centauri gradually settled into a less active mature state, the damage during those early epochs would have been catastrophic and irreversible. Whatever atmosphere this world started with faced an initial assault far more intense than current conditions, followed by billions of years of continued stripping at still alarming rates. X-ray radiation from Proxima Centauri adds another dimension to the atmospheric assault that compounds the damage from extreme ultraviolet heating. X-ray photons carry even more energy per photon than extreme ultraviolet radiation, capable of penetrating deeper into atmospheres and ionizing atoms at lower altitudes, where atmospheric density provides more targets. The X-ray bombardment we identified earlier penetrates deep into any atmosphere, ionizing molecules at altitudes where denser gas provides abundant targets for disruption. These high-energy photons emerge primarily from the star's corona, the tenuous outer atmosphere heated to millions of degrees by magnetic activity. The Sun also possesses a corona visible during total solar eclipses, but Proxima Centauri's corona is far more active and energetic relative to the star's overall luminosity. The ionization, created by X-ray absorption, has consequences beyond simple atmospheric heating. Ionized atoms and molecules become electrically charged, making them susceptible to electromagnetic forces from stellar magnetic fields and stellar wind particles. A neutral atmospheric molecule responds only to gravity and collisions with neighboring molecules. An ionized molecule additionally feels forces from any electric or magnetic fields present in its environment. This creates additional escape pathways beyond simple thermal processes. Charged particles can be accelerated by electromagnetic fields to velocities exceeding escape velocity, even when thermal energies alone would be insufficient. The stellar magnetic field extending outward from Proxima Centauri threads through any planetary magnetosphere and can directly extract ionized atmospheric constituents. The stellar wind from Proxima Centauri represents perhaps the most relentless and continuous component of the atmospheric assault. All stars produce stellar winds, continuous outflows of charged particles that stream outward through their planetary systems at velocities ranging from hundreds to thousands of kilometers per second. These winds carry mass, momentum, and magnetic field lines from stellar surfaces out to the boundaries of stellar systems and beyond. The Sun's solar wind reaches Earth at speeds of roughly 400 kilometers per second, carrying protons and electrons that interact primarily with our planet's magnetic shield, rather than our atmosphere directly. Without such protection, the consequences for any planet become severe. Proxima Centauri's stellar wind operates under the same basic physics, but with dramatically different parameters that amplify its destructive potential. Red dwarf stars with high magnetic activity produce stellar winds with much higher densities and velocities than the solar wind. The enhanced magnetic activity that drives flares also accelerates stellar wind outflow and increases the mass loss rate from the stellar surface. Estimates, based on observations and theoretical models, suggest that Proxima b experiences stellar wind pressure roughly 2,000 times greater than what Earth experiences from the solar wind. This enormous pressure compresses any planetary magnetosphere far closer to the surface than Earth's magnetic field extends, reducing the protective volume where atmosphere remains shielded from direct stellar wind interaction. Earth's magnetopause, the boundary where solar wind pressure balances magnetic field pressure, typically stands off at distances of roughly 10 Earth radii on the sunward side. This creates an enormous protective bubble within which atmospheric molecules remain shielded from direct solar wind bombardment. Only near the polar regions, where magnetic field lines connect to interplanetary space, can solar wind particles reach atmospheric altitudes. A planet experiencing 2,000 times greater wind pressure would see its magnetopause compressed to a small fraction of this standoff distance. Even if Proxima b possesses a magnetic field comparable to Earth's, stellar wind pressure would push the magnetopause so close to the planetary surface that large portions of the upper atmosphere would remain exposed to direct stellar wind interaction. The protective magnetic bubble would shrink to dimensions smaller than the atmospheric scale height, rendering magnetic shielding largely ineffective. The interaction between stellar wind and unprotected atmosphere operates through several distinct physical mechanisms, each contributing to overall atmospheric loss through different pathways. Understanding these mechanisms reveals why atmospheric stripping on Proxima b proceeds at rates no planetary process can counteract. Ion pickup occurs when stellar wind particles collide with neutral atmospheric molecules extending beyond any magnetospheric protection. These collisions ionize the atmospheric molecules, stripping away electrons and creating charged particles where neutral gas existed moments before. Once ionized, these former atmospheric molecules feel the electromagnetic forces carried by the stellar wind magnetic field. The stellar wind magnetic field, frozen into the outflowing plasma by the high electrical conductivity of ionized gas, sweeps past the planet at velocities of hundreds to thousands of kilometers per second. Newly created ions are picked up by this moving magnetic field and accelerated to stellar wind velocities within seconds. These particles are then swept away into interstellar space, carrying atmospheric mass away from the planet along with the outflowing stellar wind. Ion pickup is particularly effective at removing light atmospheric constituents like hydrogen and helium, but operates on heavier species as well. Any neutral molecule that finds itself in the stellar wind flow region will eventually be ionized by collisions or radiation and subsequently swept away. The process operates continuously whenever stellar wind flows past atmospheric gas extending beyond magnetic protection. Sputtering represents another loss mechanism, driven by stellar wind bombardment through a fundamentally different physical process. Energetic particles striking the upper atmosphere transfer momentum to atmospheric molecules through collisions, potentially knocking atmospheric constituents upward with enough velocity to escape the planet entirely. This process operates somewhat like atomic scale billiards, with incoming stellar wind particles serving as cue balls striking atmospheric molecules. A sufficiently energetic collision can transfer enough momentum to launch an atmospheric molecule on an escape trajectory, even if that molecule started at rest. The efficiency of sputtering depends on the mass ratio between impacting particles and target molecules, the impact energy, and the binding energy holding atmospheric molecules in place. Sputtering is particularly effective when stellar wind particles have been accelerated to high energies by stellar flares or shock waves in the stellar wind. During active periods, particle energies can exceed the threshold for efficient sputtering by large factors, dramatically increasing atmospheric loss rates above baseline values. Even during quiet periods, the enhanced stellar wind pressure around Proxima Centauri ensures that sputtering contributes measurably to overall atmospheric erosion. Charge exchange reactions add yet another escape pathway operating through quantum mechanical processes at the atomic level. When stellar wind protons encounter neutral hydrogen atoms in a planetary atmosphere, electrons can transfer between particles through a resonant quantum mechanical interaction. The incoming proton captures an electron from the atmospheric hydrogen atom, becoming a fast-moving neutral hydrogen atom while leaving behind a slow-moving proton. The resulting fast-moving neutral atoms are no longer confined by magnetic fields because they carry no net electrical charge. Unlike ions, which spiral along magnetic field lines and remain trapped in magnetospheric regions, neutral atoms travel in straight lines determined only by their velocity at the moment of creation. Fast neutrals created through charge exchange can escape along trajectories that would be forbidden to charged particles. This process can remove atmospheric hydrogen at rates exceeding other mechanisms under certain conditions, particularly when a significant population of neutral hydrogen extends into regions where stellar wind protons are abundant. Charge exchange operates independently of atmospheric temperature, depending instead on the overlap between neutral atmospheric gas and the incoming stellar wind flux. All of these processes operate simultaneously on Proxima b, each contributing to the overall atmospheric loss rate through distinct physical pathways. Scientists attempting to model total escape rates must account for thermal escape, driven by extreme ultraviolet heating, hydrodynamic escape during high activity periods, ion pickup by stellar wind, sputtering from energetic particle bombardment, and charge exchange reactions throughout the outer atmosphere. The cumulative effect of these processes operating together is staggering when integrated over relevant timescales. Conservative estimates suggest that Proxima b loses atmospheric mass at baseline rates, approaching 300 million tons per year, even during quiet stellar periods. During major flares, loss rates can spike by factors of hundreds, briefly stripping away mass at rates that would empty Earth's entire atmosphere within centuries if sustained. During major flares, which occur every few days on average, loss rates can spike to hundreds or thousands of kilograms per second as enhanced radiation heats the atmosphere and energetic particles strip away molecules through multiple mechanisms simultaneously. A single powerful flare might remove more atmospheric mass in hours than quiet conditions would erode in weeks or months. integrated over the planet's 4.5 billion year history, accounting for both baseline thermal escape and the catastrophic hydrodynamic losses during early stellar activity. These processes have removed atmospheric mass, equivalent to several times Earth's entire current atmosphere. Tidal locking compounds these problems in ways that affect atmospheric circulation and escape patterns across the planetary surface. Proxima b orbits so close to its parent star that gravitational forces have almost certainly locked its rotation to match its orbital period of 11.2 days. This gravitational coupling between orbital and rotational motion means that one face of the planet permanently points toward Proxima Centauri, experiencing eternal day beneath the dim red stellar disk. The opposite hemisphere faces permanently away from the star, experiencing eternal night in perpetual darkness. Temperatures on this night side plunge toward values approaching deep space background levels, limited only by whatever heat transport the atmosphere and planetary interior can provide. Between these extreme hemispheres lies a terminator zone encircling the planet in perpetual twilight, where the star hangs eternally on the horizon. This configuration creates atmospheric circulation patterns fundamentally different from the weather systems operating on Earth. Our planet's rotation distributes solar heating across all longitudes through the daily cycle, preventing extreme temperature contrasts between different regions. Earth's atmosphere circulates primarily through latitude-dependent cells, driven by differential heating between equator and poles. On a tidally locked world, the primary temperature contrast exists between the permanently heated day side and permanently frozen night side. Air heated on the day side rises and flows toward the night side at high altitudes, where it cools and sinks. This creates a global circulation pattern, with surface air flowing from the cold antistellar point toward the hot substellar point, then rising and returning aloft in a continuous cycle. Models of tidally locked planetary atmospheres reveal troubling implications for atmospheric retention that compound the direct effects of stellar radiation. The circulation pattern concentrates atmospheric molecules in certain regions, particularly around the terminator zones, where dayside and nightside air masses interact in complex ways. These convergent zones experience enhanced vertical motion as air masses with different properties collide and mix. The terminator regions may experience enhanced escape rates because atmospheric constituents are funneled upward into altitudes where stellar wind stripping operates most effectively. Vertical winds in convergent zones can lift molecules to heights where they become vulnerable to ion pickup and other loss mechanisms. The circulation pattern does not create new escape pathways, but it can enhance the efficiency of existing mechanisms by delivering atmospheric gas to vulnerable regions. The night side presents its own challenges for atmospheric stability that interact with stripping processes in complex ways. Without direct stellar heating, temperatures plunge toward values that could cause atmospheric gases to condense or freeze out onto the surface. Carbon dioxide atmospheres might partially freeze on the night side as dry ice, reducing atmospheric pressure and the protective buffer that slows escape processes. Water vapor would certainly freeze on the night side, creating a cold trap that removes water from the atmospheric circulation entirely. Any water evaporated on the warm day side would eventually migrate to the night side and freeze out permanently. This cold trapping process would remove water from atmospheric cycling, regardless of escape processes, though escaped water vapor also contributes to overall volatile loss. But all of this still fails because the fundamental problem remains unchanged, regardless of how atmosphere circulates or where gases concentrate. The stellar assault on Proxima b operates continuously across all regions of the planet through mechanisms that do not depend on local atmospheric conditions. Dayside atmosphere absorbs most of the direct radiation, but stellar wind bombardment affects the entire magnetospheric interaction region, extending around the planet. Night-side atmosphere may avoid direct heating, but stellar wind particles follow magnetic field lines that can direct them toward polar and terminator regions. No matter how atmosphere circulates between day and night hemispheres, the overall loss rate remains governed by the stellar energy input and stellar wind pressure integrated across the entire planetary surface. Atmospheric circulation might change which regions lose gas most rapidly, redistributing the loss geographically while leaving total rates unchanged. The inherent mismatch between red dwarf radiation environments and atmospheric survival operates regardless of how gases distribute themselves across the planetary surface. Scientists have searched for observational evidence that might constrain Proxima b's current atmospheric state and test theoretical predictions of atmospheric loss. Direct detection of atmospheric signatures remains beyond current technological capabilities, because Proxima b lies too close to its parent star for current instruments to separate planetary light from stellar glare with sufficient precision. Indirect methods provide some information about conditions on this distant world. Observations of stellar flare impacts on the Proxima b system show no evidence of atmospheric absorption features that would indicate a substantial gaseous envelope surrounding the planet. When flare radiation passes through a planetary atmosphere, certain wavelengths are absorbed preferentially by atmospheric molecules, creating detectable signatures in the transmitted light. The absence of such signatures suggests either no atmosphere exists, or it is too thin to produce detectable absorption. Spectroscopic observations during planetary transits could potentially reveal atmospheric signatures if Proxima b transits its star from Earth's perspective. When a planet passes in front of its star, a thin ring of atmosphere around the planetary limb filters starlight passing through it. Different molecules absorb different wavelengths, allowing atmospheric composition to be determined remotely. Unfortunately, the orbital geometry does not favor transits observable from our solar system, leaving this powerful technique unavailable for Proxima b. This leaves atmospheric characterization dependent on future technologies capable of directly imaging the planet or detecting reflected light spectra with sufficient precision to identify atmospheric features. Such observations may become possible with next-generation space telescopes designed specifically for exoplanet characterization, though even optimistic timelines place such capabilities decades in the future. What we can say with confidence based on current understanding is that the stellar assault Proxima b experiences creates conditions fundamentally incompatible with long-term atmospheric retention. The combination of extreme ultraviolet heating, driving thermal and hydrodynamic escape, X-ray ionization creating charged particles susceptible to electromagnetic acceleration, stellar flare bombardment, episodically enhancing all loss mechanisms by orders of magnitude, and enhanced stellar wind pressure, enabling ion pickup, sputtering, and charge exchange drives atmospheric escape at rates that no known planetary process can counteract over geological timescales. The closest potentially habitable world to Earth is not being gently warmed by its parent star in a nurturing embrace that might foster life. It is being actively stripped of any atmosphere it might possess through relentless processes that have operated continuously since the planet formed billions of years ago. Every day that passes sees more atmospheric mass lost to space, continuing a process of destruction that began before life emerged on Earth, and will continue until nothing remains but barren rock. Understanding whether Proxima b might somehow resist this assault requires examining what defenses a planet could potentially mount against such sustained aggression. Perhaps a powerful magnetic field could deflect incoming radiation and particles. Perhaps volcanic activity could replenish lost gases faster than stellar processes remove them. Perhaps some combination of factors might create conditions where atmospheric retention becomes possible despite the hostile stellar environment. The answer to that question proves equally devastating for any remaining hope of habitability, revealing why no plausible planetary defense can overcome the fundamental physics driving Proxima b's atmospheric destruction. Earth possesses a defense that makes complex life possible on our planet's surface. Deep beneath our feet, far below the deepest mines and oil wells humans have ever drilled, liquid iron churns through the outer core at velocities approaching 20 kilometers per year. This flowing conductive metal, heated to temperatures exceeding 4,000 degrees Celsius, generates electrical currents through its motion that create a magnetic field extending tens of thousands of kilometers into space. This magnetosphere surrounds our planet like an invisible cocoon, deflecting most charged particles from the solar wind before they can interact with our atmosphere. Without this shield, Earth would be a fundamentally different world, possibly one incapable of supporting life as we know it. The magnetic field we take for granted represents one of the most critical factors enabling our planet's long-term habitability. Understanding why Earth possesses this protection requires examining the physics of planetary magnetic field generation. Our planet's magnetic field arises from what scientists call a geodynamo, a self-sustaining electromagnetic generator powered by convective motion in the liquid outer core. The process depends on a remarkable convergence of physical conditions that Earth happens to satisfy. The outer core consists primarily of iron, with smaller amounts of nickel and lighter elements dissolved into the metallic mixture. This liquid metal layer extends from roughly 2,900 kilometers depth to approximately 5,100 kilometers depth, sandwiched between the solid silicate mantle above and the solid iron inner core below. The temperature difference between the inner core boundary and the core mantle boundary drives convective circulation, with hot metal rising and cooler metal sinking in continuous churning motion. As this electrically conductive fluid moves through existing magnetic field lines, it generates electrical currents through electromagnetic induction. These currents in turn create their own magnetic fields, which can reinforce and sustain the original field in a self-perpetuating cycle. The process requires precise conditions to operate. The fluid must be electrically conductive, it must be moving through convection, and the planet must rotate fast enough to organize fluid motion into patterns that generate coherent field structures. Earth's 24-hour rotation period provides the Coriolis forces necessary to organize convective motion into columnar structures aligned with the rotation axis. These organized flow patterns create the helical motion required for effective magnetic field generation. Slower rotation would produce weaker Coriolis forces and less organized convection, potentially preventing dynamo action entirely. Without Earth's magnetic shield, our planet would face the same atmospheric stripping processes that assault Proxima b. The solar wind would directly bombard our upper atmosphere, ionizing gases and accelerating them to escape velocity through ion pickup and sputtering. Over geological time, Earth would lose its atmosphere just as Mars lost most of its atmospheric mass after its core cooled and its magnetic field collapsed roughly 4 billion years ago. Mars serves as a cautionary example of planetary evolution without magnetic protection. Early in solar system history, Mars likely possessed a global magnetic field generated by a liquid core dynamo similar to Earth's. Evidence for this ancient field survives in the strongly magnetized crustal rocks of the southern highlands, which record field strengths comparable to Earth's current field. But Mars is smaller than Earth, and its interior cooled more rapidly. As the core solidified, convection ceased, and the magnetic dynamo shut down. Without magnetic protection, the solar wind began stripping the Martian atmosphere directly. Over billions of years, most of the original atmosphere escaped to space, leaving behind the thin carbon dioxide envelope we observe today. Mars' surface pressure currently measures less than 1% of Earth's, too low for liquid water to exist anywhere on the surface regardless of temperature. The transformation from potentially habitable world to frozen desert resulted largely from the loss of magnetic protection. The critical question for Proxima b is whether similar magnetic protection might shield its atmosphere from stellar assault. If this world possesses a magnetic field strong enough to deflect stellar wind particles and create a protective magnetosphere, perhaps atmospheric loss rates could be reduced enough to permit long-term retention. Some researchers have proposed exactly this possibility, suggesting that Proxima b might maintain habitability through magnetic shielding despite its hostile stellar environment. The physics of planetary magnetic field generation presents severe obstacles to this optimistic scenario. Magnetic dynamos require three essential conditions operating simultaneously: a conductive fluid capable of carrying electrical currents, convective motion within that fluid to drive the dynamo process, and planetary rotation fast enough to organize fluid motion into patterns capable of sustaining coherent field generation. Earth satisfies all three requirements through fortunate circumstances of planetary formation and evolution. Our liquid iron outer core provides the conductive fluid. Heat flow from the solidifying inner core and residual primordial heat drive convective circulation. Rapid daily rotation creates strong Coriolis forces that organize convection into effective dynamo configurations. Proxima b likely fails at least one of these critical requirements due to the gravitational effects of its close orbit around Proxima Centauri. The same gravitational forces that lock one planetary face permanently toward the parent star also dramatically slow planetary rotation through a process called tidal locking. Proxima b completes one rotation every 11.2 days, matching its orbital period exactly. This represents roughly 11 times slower rotation than Earth's 24-hour spin, a difference that fundamentally alters the physics of magnetic field generation. Tidal locking occurs when gravitational interactions between a planet and its star create tidal bulges that dissipate rotational energy over time. The process operates similarly to how Earth's tides gradually slow our Moon's rotation until one face permanently points toward Earth. For planets orbiting close to their stars, tidal locking occurs relatively quickly in astronomical terms, typically within a few 100 million years of planetary formation. Slower rotation means dramatically weaker. Coriolis forces organizing core fluid motion. The Coriolis effect arises from the rotation of a reference frame and produces forces perpendicular to the direction of motion. On rapidly rotating planets like Earth, these forces create the columnar convection patterns that generate coherent magnetic fields. On slowly rotating planets, Coriolis forces become too weak to organize convection effectively. The magnetic dynamos that generate planetary fields depend critically on Coriolis forces to create the helical flow patterns required for sustained field generation. Without sufficient rotation, convective motion becomes chaotic rather than organized, unable to produce the systematic electromagnetic induction needed for a self-sustaining dynamo. Models of slowly rotating planets suggest that rotation rates below certain thresholds cannot support strong magnetic dynamos, regardless of core composition or heat flow. The threshold for effective magnetic field generation remains uncertain because we have limited observational constraints on magnetic fields of slowly rotating rocky planets. However, most theoretical models place the critical rotation period somewhere between a few days and a few weeks, depending on other planetary parameters. Proxima B's 11-day rotation period falls squarely in the questionable range where dynamo action becomes marginal at best. This suggests that even if Proxima b possesses a liquid metal core with vigorous convective heat flow, its slow rotation likely prevents the generation of a strong protective magnetosphere. The planet may have possessed a magnetic field early in its history, before tidal locking completed, as rotation slowed over hundreds of millions of years. Some researchers have proposed alternative magnetic field generation mechanisms that might operate in slowly rotating planets, despite the apparent limitations of standard dynamo theory. These proposals attempt to identify conditions under which Proxima b might maintain magnetic protection, even with its 11-day rotation period. Tidal heating from gravitational interactions with the parent star represents one proposed energy source that might enhance core convection beyond what internal heat alone could provide. As Proxima b orbits, slight variations in its distance from Proxima Centauri create tidal stresses that flex the planetary interior. This flexing dissipates energy as heat, potentially warming the core and enhancing convective circulation. However, this proposal faces significant counterarguments when examined in detail. Tidal heating strong enough to substantially enhance core convection would also heat the overlying mantle, potentially reducing or eliminating the temperature gradient between core and mantle that drives convection in the first place. The same energy input that might help the dynamo could simultaneously destroy the conditions necessary for dynamo operation. Furthermore, the orbital eccentricity of Proxima b appears relatively low, based on radial velocity measurements, limiting the magnitude of tidal heating the planet experiences. Highly eccentric orbits produce much stronger tidal effects than nearly circular orbits. Proxima B's orbital parameters suggest tidal heating rates insufficient to dramatically alter core dynamics. Compositional differences in core metal content represent another proposed mechanism that might lower thresholds for dynamo action. Perhaps Proxima B's core contains different proportions of iron, nickel, and lighter elements than Earth's core, creating conditions more favorable for magnetic field generation at slow rotation rates. This proposal also faces difficulties. Compositional variations that might help dynamo action in some ways typically hurt it in others. Adding lighter elements to the core might enhance convection through compositional buoyancy effects. But those same lighter elements typically reduce electrical conductivity, weakening the electromagnetic induction that generates magnetic fields. The trade-offs involved make it unlikely that any plausible compositional variation could overcome the fundamental limitation imposed by slow rotation. Unusual core geometries represent yet another speculative possibility. Perhaps Proxima B's core has a different shape or internal structure than Earth's, creating flow patterns that generate magnetic fields through mechanisms not captured by standard models developed for our planet. This proposal remains entirely speculative, without observational constraints. We have no way to determine Proxima B's internal structure from current measurements. While unusual core geometries cannot be ruled out, invoking unknown internal configurations to rescue habitability requires abandoning scientific conservatism in favor of wishful thinking. But here is the critical point that many discussions of Proxima B magnetic fields overlook entirely. The hope that magnetic protection might save Proxima B fundamentally misunderstands what magnetic fields can and cannot do. Magnetic fields do not block all charged particles approaching a planet. They redirect particles along field lines, often funneling them toward polar regions where they can still interact with the atmosphere. Earth's auroral zones exist precisely because solar wind particles follow magnetic field lines down to atmospheric altitudes near the poles, colliding with atmospheric molecules and creating the spectacular light displays visible at high latitudes. These polar particle bombardments contribute to atmospheric loss, even on magnetically protected Earth. Ions created by auroral particle impacts can be accelerated upward along open magnetic field lines and escape into space through a process called polar wind. Earth loses atmospheric mass through its polar regions, despite possessing one of the strongest magnetic fields of any rocky planet. Magnetic fields also provide absolutely no protection against electromagnetic radiation, like X-rays and extreme ultraviolet photons. These forms of radiation travel in straight lines at light speed, completely unaffected by magnetic fields of any strength. The thermal atmospheric escape, driven by extreme ultraviolet heating, operates identically, whether a planet possesses magnetic protection or not. On Proxima b, extreme ultraviolet heating represents a major component of total atmospheric loss. The intense radiation environment heats the upper atmosphere to temperatures where significant fractions of atmospheric molecules achieve escape velocity through thermal motion alone. No magnetic field configuration can reduce this heating, because magnetic fields simply do not interact with photons. Earth's magnetic field reduces, but does not eliminate atmospheric loss through charged particle processes. Our planet still loses roughly 3 kilograms of atmospheric mass per second through mechanisms that operate despite magnetic protection, including polar wind escape and charge exchange in the outer magnetosphere. These losses remain negligible over geological time. Only because Earth's distance from the Sun keeps total energy input relatively low, and because our magnetic field is exceptionally strong by planetary standards. Proxima b would need a magnetic field far stronger than Earth's to provide equivalent protection at its much closer orbital distance. The stellar wind pressure we discussed earlier, exceeding Earth levels by enormous factors, would compress any magnetosphere far closer to the planetary surface than Earth's magnetopause extends. This enormous pressure would compress any planetary magnetosphere far closer to the surface than Earth's magnetopause extends. Earth's magnetopause the boundary where solar wind pressure balances magnetic field pressure, typically stands off at distances of roughly 10 Earth radii on the sunward side, creating an enormous protective volume within which atmospheric molecules remain shielded from direct solar-wind interaction. A planet experiencing 2,000 times greater wind pressure would see its magnetopause compress dramatically. Calculations show that even if Proxima b possessed a magnetic field equal to Earth's in strength, stellar wind pressure would push the magnetopause to altitudes below where most atmospheric escape occurs. The upper atmosphere, extending to hundreds of kilometers above the surface, would remain largely exposed to direct stellar wind interaction. The protective volume created by magnetic shielding would shrink to dimensions smaller than the atmospheric scale height. Atmospheric molecules in the thermosphere would find themselves outside magnetic protection, subject to ion pickup, sputtering, and charge exchange at rates only modestly reduced from the completely unmagnetized case. To actually protect its atmosphere from stellar wind bombardment, Proxima b would need a magnetic field roughly 10 to 100 times stronger than Earth's field. Such field strengths vastly exceed those of any known rocky planet in our solar system. Mercury generates a field about 1% as strong as Earth's. Mars has no global field at all. Venus, despite being nearly Earth's twin in size, generates no detectable magnetic field. Even the gas giant Jupiter, with its enormous metallic hydrogen interior and rapid 10-hour rotation period, generates magnetic fields only about 20,000 times Earth's strength at its surface. Jupiter achieves this through completely different mechanisms than rocky planet dynamos, using the exotic properties of metallic hydrogen under millions of atmospheres of pressure. No rocky planet with Proxima b's mass and slow rotation rate has any plausible mechanism for generating such extreme magnetic field strengths. The magnetic shield hypothesis fails not because magnetic fields are irrelevant to atmospheric protection, but because the field strengths required to make a meaningful difference vastly exceed anything a planet like Proxima b could realistically produce. Even optimistic assumptions about core composition and convective vigor cannot bridge the gap between achievable field strengths and necessary protection levels. This brings us back to the real problem that magnetic fields cannot solve regardless of their strength. The stellar radiation environment around Proxima Centauri drives atmospheric escape through multiple mechanisms, most of which operate independently of magnetic field configuration. Extreme ultraviolet photons heat the upper atmosphere regardless of magnetization. X-rays ionize atmospheric molecules regardless of magnetization. Even with the strongest plausible magnetic field, the enhanced stellar wind pressure still compresses any magnetosphere to negligible protective volumes. Some researchers, recognizing that magnetic protection cannot rescue Proxima b, have proposed an alternative defense: massive atmospheric starting conditions. Perhaps Proxima b formed with an atmosphere so enormously thick that billions of years of stripping have only partially depleted it. If the planet started with atmospheric mass equivalent to hundreds or thousands of Earth atmospheres, substantial atmosphere might remain today, despite continuous loss. This hypothesis represents a retreat from physical mechanisms to initial conditions, hoping that sheer quantity might overcome the relentless mathematics of atmospheric loss. The approach deserves careful examination because it addresses a genuine uncertainty in our understanding of planetary formation and early evolution. The hypothesis faces several fatal objections when examined against current understanding of planet formation in red dwarf systems. First, the formation conditions for planets in the habitable zones of red dwarf stars do not favor massive atmospheric accumulation. The habitable zone around a red dwarf lies very close to the star, within the region where stellar radiation significantly affects the composition and properties of the protoplanetary disk during planet formation. Proxima b formed in a region where stellar radiation would have prevented the accumulation of volatile rich material during planetary assembly. Unlike the outer regions of planetary systems where temperatures remain low enough for water, ice and other volatiles to condense, the inner zones of red dwarf systems remain too hot throughout the formation period. Planetesimals that might deliver atmospheric gases to forming planets lose their volatiles before incorporation. This limitation affects the raw materials available for atmosphere building. Earth likely received much of its water and atmospheric gases from impacts by volatile-rich bodies that formed in the outer solar system and were scattered inward through gravitational interactions with giant planets. Proxima Centauri's planetary system lacks confirmed giant planets that might scatter volatile-rich material inward, and any such material would need to survive passage through the intense radiation environment close to the star. Second, the early stellar environment was far more hostile than current conditions, which themselves are already devastating for atmospheric retention. Young red dwarf stars produce extreme ultraviolet radiation at levels 10 to 100 times greater than their mature output during extended pre-main sequence phases lasting hundreds of millions of years. Whatever atmosphere Proxima b possessed during its first few 100 million years would have experienced stripping rates correspondingly higher than current levels. The early epoch of enhanced loss coincided with the period when any accumulated atmosphere would have been most vulnerable, before the planet had time to develop whatever internal processes might contribute to atmospheric stability. This early catastrophic loss would have removed most of any primordial atmosphere before the star settled into its current activity state. Even if Proxima b formed with a massive atmospheric envelope comparable to early Venus, the enhanced stripping during stellar youth would have depleted that reservoir long before the present day. Third, and most fundamentally, the integrated loss over 4.5 billion years accumulates to amounts that dwarf any plausible starting conditions. Conservative estimates suggest current loss rates around 10 kilograms per second during quiet periods, with spikes to hundreds or thousands of kilograms per second during flares occurring every few days. Even using only the conservative quiet period estimate and ignoring enhanced early loss rates, 4.5 billion years of continuous loss at 10 kilograms per second removes approximately 1.4 times 10 to the 18th kilograms of atmospheric mass. This equals roughly 250,000 times Earth's current atmospheric mass. No plausible formation scenario delivers enough atmospheric mass to survive such cumulative loss. Even if Proxima b somehow formed with atmospheric mass equivalent to 1,000 Earth atmospheres, an extremely generous assumption, unsupported by formation models, sustained stripping at observed rates would have removed most of that mass by the present day. The mathematics of exponential loss over geological time leaves no realistic starting conditions that survive to the present as a substantial atmosphere. Volcanic outgassing represents another proposed atmospheric replenishment mechanism that deserves examination. Perhaps continuous volcanic activity pumps gases into Proxima b's atmosphere fast enough to replace what stellar stripping removes. If ongoing geological processes could maintain equilibrium between loss and replenishment, long-term atmospheric stability might be achievable despite the hostile stellar environment. Earth's volcanoes release roughly 400 million tons of carbon dioxide per year through eruptions and continuous degassing from volcanic vents. This output contributes to our planet's carbon cycle, moving carbon between atmosphere, ocean, and crust over geological timescales. Additional volcanic gases include water vapor, sulfur dioxide, hydrogen sulfide, and smaller amounts of other compounds. If Proxima b were volcanically active at similar or higher rates, perhaps equilibrium between volcanic output and stellar stripping might maintain some atmospheric stability. This hypothesis has attracted attention because it offers a potential pathway to habitability that does not depend on initial conditions or magnetic protection. The hypothesis fails when confronted with actual loss rate estimates derived from stellar observations and atmospheric escape models. Conservative calculations suggest Proxima b loses atmospheric mass continuously at rates that would drain an Earth-equivalent atmosphere within roughly 500,000 years during quiet periods alone. Accounting for flare activity reduces this timescale dramatically. Volcanic outgassing rates, capable of matching even the baseline quiet period losses, would require volcanic activity far exceeding anything observed on any planet in our solar system. Earth's total volcanic carbon dioxide output would need to increase by roughly a factor of 10 just to match quiet period loss rates on Proxima b, requiring volcanic activity more intense than anything in Earth's geological record. To maintain atmospheric equilibrium during enhanced loss from stellar flares, volcanic output would need to exceed Earth levels by factors of 100 or more during active periods. No known planetary volcanic mechanism can sustain such output rates over geological time. Even the most volcanically active body in our solar system, Jupiter's moon Io, with its continuous volcanic eruptions driven by tidal heating, does not approach the output rates required to balance atmospheric loss on Proxima b. More fundamentally, volcanic outgassing cannot replenish all atmospheric components equally. Volcanoes primarily release carbon dioxide, water vapor, sulfur compounds, nitrogen, and trace gases. The composition of volcanic emissions reflects the composition of magma sources deep within planetary interiors, which differ fundamentally from atmospheric composition. Lighter gases like hydrogen escape most rapidly from unprotected atmospheres because thermal velocities scale inversely with molecular mass. At any given temperature, hydrogen molecules move roughly 4 times faster than oxygen molecules and roughly 5 times faster than carbon dioxide molecules. This velocity advantage means hydrogen reaches escape velocity far more easily than heavier species. Even if volcanic processes maintained some heavier atmospheric constituents like carbon dioxide and nitrogen, the differential loss of lighter molecules would alter atmospheric composition in ways that might not support habitability. A world retaining only heavy volcanic gases while losing all hydrogen and water might possess some atmosphere while remaining completely uninhabitable. Water represents a particular concern that volcanic outgassing cannot address. Water molecules in Proxima b's upper atmosphere absorb extreme ultraviolet radiation and dissociate into hydrogen and oxygen atoms. The light hydrogen atoms preferentially escape due to their high thermal velocities, while heavier oxygen atoms escape more slowly through various mechanisms. This preferential hydrogen loss means that water is being permanently removed from Proxima b's system, not simply redistributed between atmospheric and surface reservoirs. Every water molecule that reaches the upper atmosphere and dissociates contributes hydrogen atoms that escape to space. No volcanic process can create new hydrogen atoms to replace those lost. Once hydrogen escapes the planet's gravitational influence, it is gone forever. Scientists estimate that Proxima b may have lost an amount of water equivalent to several Earth oceans over its 4.5 billion year history, assuming it started with significant water content. Earth's oceans contain roughly 1.4 times 10 to the 21st kilograms of water. Models of water loss from Proxima b suggest comparable or larger amounts may have escaped, depending on initial water inventory and assumptions about loss rate evolution. Even if some water remains locked in subsurface reservoirs like hydrated minerals or deep aquifers, the loss of atmospheric water vapor and the continuing escape of hydrogen atoms means that surface liquid water conditions are almost certainly impossible today. Whatever water Proxima b might still possess would be trapped in forms inaccessible to surface processes. The cold trap on the tidally locked night side might seem to offer protection for water by freezing it out of the atmosphere before it can reach altitudes where dissociation and escape occur. Water vapor migrating from the warm day side toward the cold night side would indeed freeze as temperatures drop below freezing at the terminator and beyond. However, this cold trap exacerbates water loss rather than preventing it. Water ice on the night side surface is not permanently stable. Sublimation from ice surfaces releases water molecules that can migrate back toward dayside regions through the tenuous atmosphere. Some fraction of these migrating molecules will reach upper atmospheric altitudes, where they become vulnerable to photodissociation and subsequent hydrogen escape. The cold trap merely changes the pathway of water loss rather than preventing it. Water cycles between ice reservoirs on the night side and vapor in the dayside atmosphere, but each cycle provides opportunities for molecules to reach the upper atmosphere and dissociate. Over geological time, continuous cycling through this reservoir system would eventually deliver most water molecules to altitudes where they can be destroyed and their hydrogen lost. All of this still fails because the fundamental problem remains unsolved despite examining every proposed defense mechanism. Sustained stellar radiation and stellar wind bombardment drive atmospheric escape at rates that no planetary process can counteract over geological timescales. Magnetic fields are almost certainly too weak to matter given Proxima B's slow rotation, and even strong magnetic fields cannot block the radiation driving thermal escape. Starting atmospheres would have been depleted during the early epoch of enhanced stellar activity. Volcanic outgassing cannot match loss rates, and water is being stripped away molecule by molecule through irreversible hydrogen escape. Proxima b almost certainly lacks the planetary defenses needed to protect any atmosphere from the sustained assault it experiences from its parent star. The shield is absent, and no plausible physical mechanism can provide one. Every proposed rescue scenario for this world's habitability collapses when examined against the fundamental physics of atmospheric stripping operating over billions of years. The closest potentially Earth-like world to our solar system faces a fate determined not by what defenses it might possess, but by the inescapable reality that no defense can overcome the sustained stellar violence it experiences. The question is not whether Proxima b has lost most of its atmosphere, but how completely the stripping process has advanced over 4.5 billion years of continuous operation. The final verdict requires examining what the accumulated loss means for present-day conditions on this distant world, and what implications this carries for the broader search for habitable planets around the most common stars in our galaxy. 4.5 billion years. This span of cosmic time separates Proxima b's formation from the present day, a duration so vast that human minds struggle to grasp its true magnitude. During every single second of those billions of years, stellar radiation has bombarded this planet without pause. During every moment, stellar wind has swept past, carrying away atmospheric particles into the darkness of interstellar space. During every flare erupting from Proxima Centauri's turbulent surface, enhanced energy input has accelerated escape processes beyond their already devastating baseline rates. The verdict of time has been rendered through relentless physical processes operating across geological epochs that dwarf the entire history of life on Earth. This is not a verdict that awaits future confirmation or depends on uncertain measurements. This verdict has already been delivered through billions of years of accumulated loss that no planetary process could have prevented or reversed. To understand what this timescale truly means, consider that 4.5 billion years ago, Earth itself was a molten hellscape, still cooling from the violence of planetary formation. The Moon had just formed from debris ejected by a Mars-sized impactor. No oceans existed. No continents had risen. The atmosphere consisted of volcanic gases and vaporized rock, rather than the nitrogen-oxygen mixture we breathe today. During all the time since those primordial conditions, while Earth cooled and developed oceans, while the first living cells emerged and evolved into complex organisms, while continents drifted and collided and drifted again, while dinosaurs rose and fell, and mammals inherited the planet, while human ancestors descended from trees and learned to make tools and build civilizations, during all of that incomprehensible span of time, Proxima b has been continuously losing its atmosphere to space. Consider what 4.5 billion years of continuous atmospheric stripping actually means when we account for how loss rates have varied across Proxima b's history. The conservative baseline figure of 10 kilograms per second applies only to the current relatively calm stellar state. This baseline removes roughly 300,000 tons of atmospheric mass per year, accumulating to approximately 1.4 times 10 to the 18th kilograms over the full planetary lifetime, equivalent to roughly 1/4 of Earth's current atmospheric mass. But this baseline calculation dramatically underestimates the true damage, because it ignores the catastrophic early epochs when loss rates were vastly higher. Young red dwarf stars drive hydrodynamic escape at rates millions of times greater than gentle thermal processes. During Proxima b's first few 100 million years, when Proxima Centauri blazed with extreme ultraviolet output 50 to 100 times current levels, atmospheric escape operated not molecule by molecule, but as a continuous planetary wind hemorrhaging mass into space. Models incorporating these early hydrodynamic escape phases suggest total atmospheric losses equivalent to several Earth atmospheres over the planet's history. The precise figure depends on assumptions about initial atmospheric composition and early stellar activity, but all realistic scenarios point toward the same conclusion. No atmosphere that Proxima b could have plausibly started with would survive to the present day. The mathematical reality is inescapable regardless of which specific loss rates we adopt. Time multiplied by sustained loss equals accumulated destruction. Even the most generous assumptions about initial volatile delivery and the most conservative assumptions about escape rates cannot preserve a substantial atmosphere across 4.5 billion years of relentless stripping. Whatever atmosphere Proxima b once possessed has been stripped away over geological timescales that dwarf human comprehension. This verdict becomes even more severe when we properly account for the enhanced stellar activity during Proxima Centauri's youth, a period of catastrophic loss that likely sealed Proxima b's fate within the first few 100 million years of its existence. Young red dwarf stars produce extreme ultraviolet radiation at levels far exceeding their mature output because of faster rotation rates and more vigorous magnetic activity. A newly formed red dwarf spins rapidly, having contracted from a larger protostellar cloud while conserving angular momentum. This rapid rotation drives intense magnetic dynamo action, creating surface magnetic fields far stronger and more chaotic than those of older, slower spinning stars. Models of red dwarf stellar evolution suggest that Proxima Centauri's extreme ultraviolet output was roughly 50 times higher when it was 100 million years old compared to its current mature state. Some models predict even larger enhancement factors during the earliest epochs, when the star was still contracting toward its main sequence configuration. At these enhanced radiation levels, atmospheric escape from Proxima b would have operated in the hydrodynamic regime we examined earlier, with the upper atmosphere flowing continuously outward into space, rather than losing molecules through gradual thermal processes. The escape rates during this epoch would have exceeded current values by factors of thousands, making any atmospheric retention essentially impossible. This early epoch of catastrophic loss represents a period when atmospheric destruction proceeded at its most rapid pace, precisely when any newly formed atmosphere would have been most vulnerable. A planet cannot accumulate a protective atmosphere while losing mass faster than any source can supply it. Proxima b faced a losing battle from the moment of its formation. The duration of this enhanced loss phase compounds its devastating impact. Red dwarf stars remain in heightened activity states for hundreds of millions of years as they gradually spin down through magnetic braking. Proxima Centauri likely maintained extreme ultraviolet output at 10 or more times current levels for the first billion years of its existence, only gradually declining toward present-day values. During this extended danger period, hydrodynamic escape and enhanced thermal loss would have removed most of any primordial atmosphere the planet possessed. By the time Proxima Centauri finally settled into its current activity state, Proxima b would have already lost the vast majority of whatever volatile inventory it started with. The subsequent billions of years of loss at lower but still significant rates simply continued removing whatever remnants survived the early catastrophe. This brings us back to the real problem that dominates all discussions of Proxima b's habitability. The atmospheric stripping that condemns this world operates not as a future threat that might somehow be avoided, but as an accomplished fact extending back to the earliest epochs of planetary history. The damage was largely done before life had even emerged on Earth. Everything since has simply continued a process of destruction that was essentially complete billions of years ago. The implications for planetary surface conditions are devastating and leave no room for optimistic interpretation. Without substantial atmospheric pressure, liquid water cannot exist on a planetary surface regardless of temperature. This fundamental constraint of physics eliminates the possibility of surface habitability, even if temperatures somehow fell within ranges compatible with liquid water. Water exists in three phases: solid ice, liquid water, and gaseous vapor. The transitions between these phases depend on both temperature and pressure. At atmospheric pressures typical of Earth's surface, water transitions from ice to liquid at 0 degrees Celsius and from liquid to vapor at 100 degrees Celsius. But at lower pressures, these transition temperatures change, and below a critical pressure threshold, the liquid phase becomes impossible entirely. This critical threshold lies at approximately 612 pascals, known as the triple point pressure of water. Below this pressure, water transitions directly from solid ice to gaseous vapor through sublimation, skipping the liquid phase entirely regardless of temperature. Mars demonstrates this principle with surface pressures averaging only 600 pascals, right at the threshold where liquid water becomes marginally possible under ideal conditions, but practically absent across most of the planetary surface. If Proxima b has lost most of its atmosphere to space over billions of years, surface pressures would have fallen far below the triple point threshold. Any water ice remaining on the surface would slowly sublime into the thin atmosphere, with water vapor molecules eventually reaching altitudes where they become vulnerable to photodissociation and hydrogen escape. The planet cannot maintain liquid water not because temperatures are wrong, but because pressure conditions make the liquid phase physically impossible. The loss of water compounds the habitability problem beyond simple atmospheric pressure considerations. Water serves as the fundamental solvent for biochemistry as we understand it, providing the medium in which biological molecules interact, fold, and perform their functions. Without liquid water, the complex chemical reactions that underlie biological processes cannot occur in any form we recognize as life. Every known living organism on Earth depends on liquid water for essential biochemical functions. Proteins fold correctly only in aqueous environments. DNA replicates through processes requiring water as both reactant and medium. Remove liquid water, and the entire edifice of biochemistry collapses into chemical inactivity. Even if some theoretical life form could survive without liquid water, such organisms would face constant bombardment by stellar radiation that penetrates directly to the surface when no atmosphere provides shielding. The same extreme ultraviolet photons that strip atmosphere also carry enough energy to break biological molecules directly. Ultraviolet radiation damages biological systems through multiple mechanisms. It breaks chemical bonds in DNA, creating mutations and triggering cell death. It denatures proteins by disrupting their carefully folded structures. It generates reactive oxygen species that damage cellular membranes and other components. On Earth, our atmosphere absorbs virtually all extreme ultraviolet radiation high in the stratosphere, protecting surface life from this invisible assault. On a world without atmospheric protection, the extreme ultraviolet radiation reaching the surface would sterilize exposed areas within minutes to hours. The radiation flux from Proxima Centauri at Proxima b's orbital distance exceeds Earth levels by factors approaching 1,000. No known organism could survive direct exposure to such intense radiation, regardless of any other adaptations it might possess. DNA, proteins, lipids, carbohydrates, nucleotides, amino acids. The fundamental building blocks of known life forms would be rapidly destroyed by radiation levels thousands of times greater than anything terrestrial organisms have evolved to withstand. The surface of an airless Proxima b would be as sterile as a hospital autoclave, continuously bathed in radiation lethal to any conceivable biology. Even if life somehow emerged on Proxima b during an early epoch when atmospheric conditions were more favorable, that life would have faced a steadily deteriorating environment as atmospheric shielding diminished over geological time. The surface radiation flux would have increased gradually as atmosphere was lost, eventually crossing thresholds beyond which surface survival became impossible. Any organisms restricted to surface environments would have been driven to extinction as radiation levels increased beyond survival thresholds. Unlike Earth, where atmospheric composition has remained within habitable ranges for billions of years, Proxima b offered a constantly worsening environment that would have pushed any surface biosphere toward inevitable extinction. Subsurface refugia offer the only potential habitat where life might theoretically persist on Proxima b today. Deep underground, rock layers would shield any hypothetical organisms from surface radiation. The same material that blocks light from penetrating into caves would block lethal ultraviolet radiation from reaching subsurface environments. Geothermal heat from radioactive decay and residual primordial heat might provide energy sources for chemosynthetic metabolisms independent of surface conditions. Earth hosts thriving ecosystems in deep mines and around hydrothermal vents where organisms derive energy from chemical reactions rather than sunlight. Similar metabolic strategies could theoretically operate on Proxima b if appropriate chemical gradients exist in the subsurface. Liquid water might even exist in deep aquifers if any water remains in the planetary interior after billions of years of surface loss. Geothermal heating could maintain temperatures above freezing at sufficient depths, and pressure from overlying rock would easily exceed the triple point threshold, allowing liquid water to exist in underground reservoirs. But even this subsurface habitability scenario faces constraints that make long-term survival unlikely. Without atmospheric cycling of water and other volatiles, subsurface reservoirs would represent finite resources that deplete over geological time through various loss mechanisms. Water slowly escapes from any planetary interior through volcanic outgassing and diffusion through rock. On Earth, atmospheric and oceanic water cycles constantly replenish subsurface reservoirs through infiltration and hydration reactions. Rain falls, soaks into soil, percolates through rock layers, and recharges underground aquifers. This cycling maintains subsurface water availability over geological timescales. On a world without substantial atmosphere, no such replenishment occurs. Subsurface water reservoirs would represent isolated deposits, gradually diminishing through outgassing and other loss processes. Any subsurface life would exist in isolated pockets, slowly losing the resources needed for survival, with no prospect of long-term sustainability. Volcanic outgassing might replenish some volatiles from the planetary interior, but not at rates sufficient to maintain long-term habitability against both surface escape and biological consumption. Any subsurface biosphere would face resource limitations that surface life on Earth never encounters, confined to shrinking oases of habitable conditions within an increasingly hostile planetary interior. More fundamentally, the absence of surface habitability eliminates the possibility of biosphere development as we understand it from Earth's history. Our planet's life emerged in surface or shallow subsurface environments where energy and nutrients were abundant. Only later did life colonize diverse ecological niches, including the deep subsurface environments that might persist on Proxima b. The energy input from solar radiation drives photosynthesis that forms the base of Earth's food chain, supporting virtually all complex life through direct consumption of photosynthetic organisms or consumption of organisms that eat photosynthesizers. Remove surface photosynthesis, and you remove the energy foundation supporting most of Earth's biosphere. Without comparable energy input on Proxima b's surface, any life would be restricted to chemosynthetic metabolisms that typically support far less biological productivity than photosynthesis-based ecosystems. Earth's chemosynthetic communities around hydrothermal vents are fascinating and diverse, but they support biomass densities orders of magnitude below photosynthesis-supported ecosystems. A planet restricted to chemosynthesis would be biologically impoverished, even in the best scenarios. What does Proxima b likely look like today after 4.5 billion years of atmospheric stripping? The most probable scenario based on atmospheric escape calculations is a world resembling Mercury or our Moon more than Earth or even Mars. The surface would be directly exposed to space, experiencing the full intensity of stellar radiation without atmospheric filtering or absorption. Extreme temperature variations would exist between the permanently illuminated day side and the permanently dark night side, with no atmospheric heat transport to moderate the contrast. The dayside temperature would reach approximately 400 degrees Kelvin if the planet has low surface reflectivity, hot enough to melt some metals like lead and tin, but not extreme, compared to Mercury's dayside temperatures exceeding 700 degrees Kelvin. The dimmer illumination from Proxima Centauri compared to sunlight limits maximum temperatures despite the closer orbital distance. The night side would plunge toward temperatures approaching the cosmic background of 3 degrees Kelvin without any atmospheric heat transport from the illuminated hemisphere. In practice, heat conduction through the planetary crust and any residual atmospheric traces would maintain night-side temperatures somewhat above absolute zero, perhaps in the range of 50 to 100 degrees Kelvin. Still, the thermal contrast between hemispheres would be extreme by terrestrial standards. The terminator zone between eternal day and eternal night would experience intermediate temperatures, but extreme thermal gradients across relatively short horizontal distances. Walking from the day side toward the night side, an observer would experience temperature drops of hundreds of degrees over distances measured in kilometers, creating material stresses that might fracture surface rocks and create unique geological features. The surface itself would be heavily cratered from billions of years of meteorite impacts, without atmospheric ablation to protect against smaller impactors. Unlike Earth, where most small meteoroids burn up in the atmosphere, an airless Proxima b would accumulate impact craters down to very small sizes, creating a surface texture similar to the Moon's highland regions. Alternatively, if Proxima b retained some thin atmospheric remnant despite billions of years of stripping, or possesses surface volatile deposits from cometary impacts or outgassing, conditions might more closely resemble Mars. A tenuous atmosphere of carbon dioxide might provide minimal pressure, perhaps a few hundred pascals, without meaningful radiation shielding or thermal regulation. Surface ice deposits might exist in permanently shadowed craters near the terminator or on the frozen night side, representing frozen remnants of the planet's original volatile inventory. These deposits would slowly sublime over geological time, feeding molecules into the thin atmosphere where they eventually escape to space, but the process might be slow enough that some ice persists to the present day. Neither scenario permits conditions where life as we understand it could emerge, evolve, or persist over geological timescales. The verdict of atmospheric stripping condemns Proxima b to long-term sterility, regardless of its initial conditions, current state, or any plausible future developments. This conclusion extends beyond Proxima b to challenge broader assumptions about habitability around red dwarf stars that have shaped exoplanet research priorities for decades. The implications ripple outward from our nearest stellar neighbor to encompass the most common stellar type in our galaxy. Red dwarf stars represent roughly 70% of all stars in the Milky Way, a dominance that initially seemed to promise abundant opportunities for finding habitable worlds. These small, cool, long-lived stellar furnaces vastly outnumber Sun-like stars, which comprise only about 7% of the stellar population. For every star like our Sun, there exist roughly 10 red dwarfs scattered throughout the galaxy. The longevity of red dwarfs added to their appeal as potential life-hosting systems. While our Sun will exhaust its hydrogen fuel in roughly 5 billion years, red dwarfs burn so slowly and efficiently that they can shine for trillions of years, hundreds of times longer than the current age of the universe. This extended stellar lifetime seemed to offer enormous windows for biological evolution to proceed, potentially giving rise to civilizations far older and more advanced than anything possible around short-lived massive stars. The sheer number of red dwarf systems seemed to promise that even if habitable planets were rare around any individual star, the total count of habitable worlds in red dwarf systems should dominate the galactic census. Statistical arguments suggested that most habitable planets in the Milky Way should orbit red dwarfs, simply because red dwarfs are so enormously abundant. Atmospheric stripping physics undermines this optimistic reasoning at its foundation. The same characteristics that make red dwarfs numerous and long-lived also make them fundamentally hostile to planetary atmospheres in ways that cannot be overcome through planetary properties or formation conditions. Red dwarfs produce less total luminosity than Sun-like stars, which initially seems advantageous for habitability by reducing the radiation assault on nearby planets. But this reduced luminosity requires planets to orbit much closer to receive sufficient energy for liquid water temperatures. The habitable zone around a red dwarf lies at orbital distances measured in millions of kilometers, rather than the 100 million kilometers separating Earth from the Sun. At these close distances, stellar radiation intensity per unit area actually exceeds what Earth receives from the Sun in the most damaging high-energy wavelengths. Red dwarfs produce a larger fraction of their total output as extreme ultraviolet and X-ray radiation compared to Sun-like stars, and the proximity of habitable zone planets amplifies this already elevated flux. The magnetic activity of red dwarfs compounds the radiation problem through frequent energetic flares that would be extraordinary events if they occurred on our Sun. The fully convective interiors of red dwarfs generate chaotic magnetic field configurations that store and release energy through flare events far more frequently than the organized magnetic cycles of larger stars. Planets in the habitable zones of red dwarf stars face a fundamental dilemma that admits no resolution. They must orbit close enough to receive sufficient energy for liquid water temperatures, but this proximity subjects them to atmospheric stripping rates that remove any atmosphere over geological time. The habitable zone becomes a killing zone, where planets may briefly possess habitable conditions before losing them to sustained stellar assault. Some researchers have proposed that planets around the quietest red dwarf stars might avoid the worst atmospheric stripping and retain habitable conditions. Not all red dwarfs are as violently active as Proxima Centauri. Some show lower flare rates and reduced high-energy emission in current observations. Perhaps planets orbiting these calmer stars might retain atmospheres long enough for life to emerge and evolve. This proposal faces a decisive counterargument rooted in stellar evolution. Stars that appear quiet today were not necessarily quiet in their youth when planetary atmospheres were forming, and when life might have first emerged. The critical early epochs, when atmospheric retention was most important, coincided with periods of enhanced stellar activity, regardless of current conditions. All red dwarfs pass through extended phases of elevated magnetic activity as they spin down from their rapid initial rotation. The damage from early atmospheric stripping cannot be undone by later stellar quiescence. A planet that lost its atmosphere during the first billion years of its existence cannot recover that atmosphere simply because its star eventually became less active. Moreover, even the quietest red dwarfs produce extreme ultraviolet and X-ray emission at levels substantially exceeding what solar-type stars deliver to their habitable zones. The fundamental physics of red dwarf stellar structure, with fully convective interiors generating persistent magnetic activity, creates high-energy emission as an unavoidable byproduct of red dwarf existence. Planets orbiting red dwarfs will always face elevated atmospheric stripping rates compared to planets orbiting Sun-like stars at equivalent effective temperatures. The question is not whether stripping occurs, but only how rapidly it proceeds, and how completely it destroys atmospheric stability over planetary lifetimes. The verdict of time that condemns Proxima b extends as a warning about red dwarf habitability generally. The closest star system to our own provides a detailed case study demonstrating the fundamental incompatibility between red dwarf stellar physics and long-term planetary atmospheric retention. Other red dwarf systems face similar constraints, even if the specific loss rates and timelines differ in quantitative detail. This realization transforms our understanding of where to search for life beyond Earth, and redirects the priorities that should guide exoplanet research. The abundance of red dwarf stars initially suggested they should host the majority of habitable worlds in the galaxy. Atmospheric stripping physics suggests instead that red dwarf systems are fundamentally hostile to the kind of long-term atmospheric stability that complex life seems to require. Sun-like stars, despite being far less common than red dwarfs, may provide the only stellar environments where rocky planets can maintain atmospheres over the billions of years needed for life to emerge and evolve from simple chemistry to complex organisms. The habitable zones of Sun-like stars lie far enough from their parent stars that radiation intensity remains manageable, and the lower magnetic activity of these larger stars produces fewer and less energetic flares. Our own solar system, previously considered merely one of countless similar arrangements scattered throughout the galaxy, may represent a relatively rare configuration where conditions permit long-term habitability. The stability of our Sun, its moderate radiation output, and the comfortable distance of Earth's orbit combine to create conditions that may be far less common than the simple abundance of potentially habitable zone planets initially suggested. Proxima b teaches us that proximity and habitable zone location are insufficient for true habitability. A planet can sit exactly in the theoretical habitable zone of its star and still be completely incapable of supporting life, because the stellar environment does not permit atmospheric retention over geological time. The stellar context matters as much as the planetary properties. We are left contemplating a world that briefly inspired dreams of nearby life and interstellar exploration, now revealed as a casualty of stellar violence operating across cosmic timescales. The announcement of Proxima b's discovery sparked genuine excitement about the possibility that our nearest stellar neighbour might host a world where life had emerged, or where future human explorers might someday walk beneath alien skies. That excitement has given way to a more sober understanding of what Proxima b actually represents. This world is not a cradle awaiting the emergence of life. It is not a potential destination for future colonization. It is not evidence that habitable worlds are common in the cosmos. It is a corpse, or perhaps more accurately, a world that was never permitted to become truly alive in the first place. Proxima b is being stripped bare. It has been stripped bare since its formation 4.5 billion years ago. The process continues today as stellar radiation and wind carry away whatever atmospheric remnants still cling to this world. The process will continue until nothing remains but barren rock beneath empty skies, orbiting its red dwarf host until the star itself finally exhausts its fuel trillions of years in the future. The closest potentially Earth-like world to our solar system serves as a monument to the harsh realities of planetary habitability in a universe governed by physics rather than hope. Not every world in a habitable zone is habitable. Not every rocky planet can maintain conditions for life. The universe contains countless worlds where the physics of stellar radiation and atmospheric escape combine to preclude the emergence of biology, regardless of orbital parameters or initial conditions. Proxima b cannot retain a stable atmosphere over geological time. This is not speculation about uncertain future scenarios that might unfold differently than we expect. This is not a preliminary conclusion, awaiting better observations that might reveal unexpected protective mechanisms. This is the verdict rendered by physical processes that have operated continuously since the planet formed, processes we understand well from studying our own solar system, and that operate according to laws of physics applicable throughout the cosmos. The atmospheric stripping that dooms this world to perpetual sterility is not a future threat, but a present reality and an ancient history extending back billions of years. The verdict was rendered long ago. We are simply recognizing its implications now that we have discovered this world and understood its stellar environment. We must look elsewhere in our search for life beyond Earth. The nearest star offered what seemed like our best opportunity for finding a second home or alien neighbors close enough to study in detail, or perhaps someday visit. Instead, it offers a lesson about the severe constraints that stellar physics places on planetary habitability. The universe may be far lonelier than our early optimism about Proxima b suggested, with truly habitable worlds far rarer than the raw count of potentially habitable zone planets implies. The closest world is being stripped bare. That process began before life emerged on Earth, and will continue long after our own planet has been consumed by our dying sun 5 billion years from now. Across the gulf of 4 light-years of interstellar space, Proxima b orbits in silent testimony to the destructive power of stellar radiation and the relentless verdict of geological time. No magnetic field protects this world. No volcanic process replenishes its lost atmosphere. No primordial reservoir of volatiles survived the early catastrophe of enhanced stellar activity. The planet exists as an example of what becomes of worlds in the killing zones around red dwarf stars, worlds that might have been habitable in some theoretical sense, but that physics condemns to eternal sterility. The search for life continues, but it must continue with clearer eyes about where life might actually be found. Proxima b has taught us that the universe is not arranged for our convenience, that the nearest potentially Earth-like world is not Earth-like at all in the ways that matter most, and that habitability requires conditions far more specific than simply orbiting at the right distance from any available star. Somewhere in the cosmos, worlds may exist where conditions permit the emergence and long-term survival of life. Those worlds almost certainly do not orbit red dwarf stars. They orbit sun-like stars at comfortable distances where atmospheric retention is possible over the billions of years required for biological evolution. They possess magnetic shields, stable stellar environments, and the accumulated good fortune of circumstances we are only beginning to understand. Proxima b is not one of those worlds. It never was. It never could have been. The verdict of time, rendered through 4.5 billion years of relentless atmospheric stripping, admits no appeal and offers no hope of reversal. Our nearest cosmic neighbour is a world being stripped bare, and understanding why teaches us something profound about the conditions required for life in a universe that creates planets abundantly but nurtures them rarely.